Hello friends, welcome back to the time history analysis. Today we shall be discussing the nonlinear time history analysis as per Newmark method. Current motion record can be having some interval of record which is called record interval, and this is subdivided into sub steps so that we get more accuracy, and each sub steps is called the step size delta t. And we have seen earlier that the Newmark method can be either linear acceleration method, where from first station to the next station the acceleration varies linearly, assumed to be varying linearly, and it can be constant acceleration method when between two stations an average value of the acceleration is supposed to remain constant between the two stations. We have also seen it could be average acceleration method when gamma is half and beta is 1/4. Linear acceleration method when gamma is half and beta equal to 1/6. A linear system is this where response is linear, and nonlinear system is where the stiffness, initial stiffness is changing. The change may be twice, thrice or any times, or it can be even curvilinear where every step it is changing its stiffness. So we have to understand that the basic difference between the linear method and nonlinear method is that the stiffness is changing at some time. It will change at a point which is called the event point. So this is event point here, event point here. At the event point the stiffness is changing, and you have to keep track where it is changing and it is changing to what value. This is the basic difference between the linear method and nonlinear method. So nonlinear system stiffness will change. You have to keep track of the stiffness and stepwise summation of force you have to get. You apply this method to any system and give it an excitation. You apply the time step analysis as per Newmark and get the response. So response will be displacement response, velocity response and acceleration response. We are making a difference between here the normal stiffness and the second stiffness. Normal stiffness is the slope of the initial response line, force deformation line, which is given by tan theta, force divided by corresponding deformation. In the nonlinear system, that will not hold good because it is not linear and elastically Hookean system. So we take any point and join the origin, then this line is called the second slope. So corresponding stiffness, the tangent of that angle, if the angle is alpha, then tan alpha is the second stiffness for the system, which is equal to force at this system F dash divided by corresponding displacement delta dash. So in the nonlinear analysis we shall be depending on the second stiffness. Here we are showing two steps. These are in the sub steps. So from ui to ui plus 1, the difference in the displacement is delta ui and difference in the time is delta t. So you see here initial tangent line is going in this direction, the initial tangent stiffness ki t, but since because of nonlinearity the point has gone here, and if I join this first point and the second point, the slope of this line is the second stiffness. So if you can take the stiffness at that point and name it as ki and multiply it by this delta ui distance, then you get the delta fsi, the increment in the spring force, increment in the spring force. This spring force will be changing at every step as the nonlinearity goes on, and it goes into different new steps. So what is the current spring force if you want to get? Then the previous spring force plus the increment in the spring force you have to add up. So in the current step, the increment in this spring force will be current stiffness ki into increment of the displacement delta ui. The equation of motion is mu double dot plus cu dot plus ku equal to ft. For the ith time station, I can put the suffix I for all the parameters, and ku is spring force, so I am writing here as fsi. External force is fti. For I plus 1 station, it becomes with the parameters with suffix I plus 1. So from this second equation, I can get this expression for ui plus 1 double dot, that is acceleration in the new step. Acceleration in the new station is given by this expression, this divided by m from equation 2. This we shall be utilizing in the process. Now let us see the steps involved in the nonlinear analysis as per Newmark. So we start with the equation of motion, and if you want to get the initial conditions, simply rearrange the equation with u double dot naught, that is at t equal to 0 condition, and you get this. So this is the initial acceleration if there is any value of ft or velocity or displacement initially given. If these are 0, then initial acceleration will be also 0. Then we are selecting a suitable time step size and select gamma and beta. That is, we want to select whether it is linear acceleration or constant average acceleration method. As earlier, you calculate these two constants, a small and small b, and c is your damping coefficient. So you start with this time step size with one step, ith step. So increment in the force is already given. This ft function is given to you. So delta fi you can calculate. This delta fi can be calculated, the increment in the external force in the current time step, and delta fi bar is the effective force in that time step. So it is given by this expression. At every end of every step, you find out what is the current stiffness. In the beginning, it can be same as the previous stiffness, but at some time where event takes place, there will be change in the stiffness. So you will keep track of that stiffness. The effective stiffness K bar is given by Ki plus this effect of damping and effect of mass. Now once I know the effective increment in the force and effective stiffness, then increment in the displacement delta ui is effective force by effective stiffness, very simple. And the increment in the velocity is given by this expression involving those known parameters. As I said, the new spring force equal to old spring force plus increment in the spring force. Increment in the spring force is current K into increment of displacement in the current step, so delta ui. At the end of this much analysis, you update your displacements and velocity. New displacement ui plus 1 is previous displacement ui plus increment in the displacement delta ui. New velocity u dot I plus 1 equal to previous velocity u dot I plus increment in the velocity delta ui dot. The new acceleration is obtained from the equilibrium equation. So if you look at the previous page, this expression is available already. Fi plus 1 minus c u dot I plus 1 minus fs I plus 1 divided by the mass. After this calculation, the values at the new time station I plus 1th station is known, and now we repeat this step 2 and go to the next steps. We have taken a numerical example from A.K. Chopra's book. This example, this excitation we had taken also in our previous slide for numerical linear analysis. So it is a half sinusoidal excitation. The ordinates are given at time step size 0.1. In our analysis also, we shall be keeping the same time step size 0.1 second. We have taken a single degree of freedom system having a mass, having a stiffness, and having some damping. The values are given here: mass equal to 0.2533, K equal to 10, time period initially is 1 second, and Xi equal to 0.05, that is corresponding to concrete structures. The units are not given here because this should be in the consistent unit only. You can take any unit corresponding for all the parameters in the same unit. Now the excitation is given here, which is not linear. In the beginning it is linear, where stiffness is K equal to 10, and then here the stiffness is different. Here it is a flat line in the response, so stiffness is 0, and again after some time it will reverse and stiffness will be regained as K equal to 10 hypothetically. and the process will continue. This is called elastic, perfectly plastic system. Initially elastic, then it is fully plastic. Fully plastic has stiffness 0. Now where it will yield, this should be supplied to you. So it is yielding at the point 0.75 unit of displacement. So you look at your displacement, whenever it reaches this value 0.75 unit, you understand that the stiffness has changed and my new stiffness will be K equal to 0. Where it will change to the reversal, that also you can find out gradually by noting the velocity of the system. At this point velocity will be 0, and then immediately next point after one time step it will become negative. So I can understand when it is reversing the sign of the velocity, and I understand it is changing the stiffness once again, K equal to 10 hypothetically, and it reverses its hysteretic behavior. And this loop will continue so long as you go on exciting the system. We make a little initial calculations. We find the omega K by m, which can be readily calculated. C is not given, so C can be obtained from twice j omega m. These parameters are already available with us, so C is this much. And we are considering average, constant average acceleration method, so gamma equal to half and beta equal to 1/4. Initially the value displacement is 0, velocity is 0, and initial force is also 0. The half sinusoidal excitation starts at t equal to 0, f equal to 0. So initial acceleration from the equilibrium equation comes out to be 0. We are taking time step size same as that of the record interval here for the sake of convenience in our calculation. So delta t equal to 0.1. We calculate the constant A and constant B, and we calculate also those expressions which you have seen in the previous slides. Delta Fi bar, as per the standard one is this, and putting the value of A and B, we get this is the expression which we shall be utilizing in our steps. The effective stiffness K bar is given by this expression. So after putting the known values of the constants, I get simplified expression Ki plus 104.504. So we start the time step size here. We find the increment in the displacement delta Fi bar divided by K bar. Increment in the velocity is given by this expression, which can be simplified, and it comes out to 20 delta ui minus 2 ui dot. At the end of this, you get the new values of the displacement ui plus 1, ui plus delta ui, new velocity u dot I plus 1 equal to u dot I plus delta u dot I. And acceleration in the new time station is obtained from the equilibrium equation, as we have discussed in the previous slide. Now we start a numerical, the same numerical we have shown there. So corresponding expressions I have again taken here for easy understanding. K bar is given through this expression, delta Fi bar and delta ui delta Fi bar by K bar, the increment in the spring force through this, and the increment in the velocity by this, and final expression of the acceleration is given through this expression. So initially at time equal to 0, all the parameters are 0 except this Ki, which is 10 in the beginning also. So at this step there is no function of, no play of K bar, so we are taking K bar as 10, or you can just keep it blank. Go to next time station, 0.1 second. My force is increased to 5 from the half sinusoidal excitation given. The value is 5 here at 0.1 second. So increasing the external force is 5 minus 0, 5, and initial stiffness remains same, so 10, and K bar from this expression comes out to be 104.5.0. So from this expression you can get the delta Fi bar. Calculate this comes out to be this. Delta U bar from this expression comes out to 0.0437 units. Spring force will be nothing but delta ui multiplied by current stiffness 10. So 10 into this, it comes 0.4367. So FSI, new spring force, equal to previous spring force, which is 0, plus increase in the spring force, which is this. So this expression is equal to this previous spring force plus increase in the spring force in the between the two time steps. So this is obtained, no problem. The expression for increasing the velocity is through this, comes out to be this. And here you can update your displacements and velocity. This displacement here is the previous displacement plus increase in the displacement as given here. So it is 0.0437. New velocity equal to previous velocity plus increase in the velocity which is available here, 0.8733. So it is 0.8733. Acceleration is given through this expression. This should be I plus 1. This is wrongly written here. So u double dot I plus 1 is through this expression. I get this equal to this. I come to next time step, which is 0.2 second time, and the excitation ordinate is 8.66 units. So increase is 8.66 minus 5 is 3.66. Now whether the stiffness is changing. Now you look at the displacement here. It is 0.2326, which is less than 0.75. So stiffness will not change. It has not yielded. K bar I get, then delta Fi bar, then other parameters from the expressions we got earlier, and final acceleration I write here. Similarly, when at 0.3 second the same steps goes on, the stiffness remains 10 because the displacement here is 0.6120 less than the yield displacement. However, when you go to time step 0.4, your displacement you look to be 1.1275. What does it indicate? It indicates it has already yielded when the displacement was 0.75 units. So the initial stiffness Ki, current stiffness is become 0 now. It is elastic, fully plastic. So current stiffness is 0. And the same steps you continue. You see here, this velocity is changing here. It was 0.80 here and here it is negative. So in between, because of the change of the velocity, the stiffness has changed. So stiffness comes from 0 to 10. This you have to see from the sign of the velocity. And the steps continues. We have gone up to 1 second. You can go further. Up to 0.6 second, it is what is called forced vibration. Beyond that, 0.7 second, 0.8 second, 0.9 second and 1 second, these are all free vibrations under the impact of the excitation given up to 0.6 second. Now let us see the graphs for this displacement, velocity and acceleration. They look like this. Displacement is the blue one, velocity is the red one, and acceleration is the black one. Displacement has less zigzagness, almost smooth. This is blue one, displacement, less zigzagness. Velocity is red one, having slightly more zigzagness, and acceleration having lot more zigzagness, and it is fluctuating. So displacement, velocity and acceleration graphs are given here. Thank you very much for coming with me up to here. Please subscribe the channel, like and share the videos, put your comment on the comment box and inquiries also in the comment box. I'll try to answer your queries to the best of my ability. Thank you.